Hello students, good morning. I am Dr. A.K.SINHA, Professor of Chemistry. Today I will continue from the last class. Last class I was discussing fundamentals of chemical thermodynamics. Now I will continue. Actually I am reviewing the fundamentals of energetics and chemical thermodynamics, and I have discussed many terms like internal energy, enthalpy change, sign convention, expression for the work of expansion, first law of thermodynamics, and a mathematical formula for the first law of thermodynamics. Now I will continue other terms. Calorific value. The calorific value. What is the calorific value? The calorific value of a fuel or food is the amount of heat in calories produced from the complete combustion of 1 gram of the fuel or food. Again I am repeating, the calorific value of a fuel or food is the amount of heat in calories produced from the complete combustion of 1 gram of the fuel or food. What is the heat of formation? Next term is heat of formation. Heat of formation is the amount of heat evolved or absorbed when 1 mole of the compound is formed from its element. When all the substances are taken in their standard state, that is the 298 Kelvin and 1 atmospheric pressure, it is called a standard heat of formation. Heat of formation is the amount of heat evolved or absorbed when 1 mole of the compound is formed from its elements. When all the substances are taken in their standard state, that is 298 Kelvin and 1 atmospheric pressure, it is called a standard heat of formation. What is heat of neutralization? Heat of neutralization is defined as the amount of heat evolved when 1 gram equivalent of the acid is completely neutralized by the base, or 1 gram equivalent of base is completely neutralized by the acid. What is its value? Heat of neutralization of a strong acid by a strong base. What is its value? Heat of neutralization of a strong acid by the strong base is always constant, and it is equal to 57.1 kilojoule per mole. Again I am repeating, heat of neutralization of a strong acid by a strong base is always constant and equal to 57.1 kilojoule per mole. If one or both of them are weak, the heat of neutralization is less because a part of heat is used up for the dissociation of the weak acid or weak base. What is the heat of hydration? Heat of hydration. It is the amount of heat evolved or absorbed when 1 mole of an anhydrous salt combined with the required number of water molecules to form the hydrated salt. Here you should know that anhydrous and hydrated. Anhydrous means without water and hydrated means with water. Then heat of hydration is the amount of heat evolved or absorbed when 1 mole of an anhydrous salt combines with the required number of water molecules to form the hydrated salt. Example, copper sulfate, solid copper sulfate. It is anhydrous, no water molecules. But this copper sulfate solid plus 5H2O, that is the water is liquid. It gives CuSO4 5H2O, blue vitriol. It is copper sulfate 5H2O is also called blue vitriol. Then copper sulfate solid plus 5H2O, that is the liquid. It gives CuSO4 5H2O. And what is energy heat? Then delta H is equal to minus 78.2 kilojoule. Delta H value is equal to minus 78.2 kilojoule. Minus means heat will evolve. It will release in the process. Heat will be released. Means when copper sulfate will absorb 5 moles of H2O, then it will form CuSO4 5H2O, and heat evolved will be delta H is equal to minus 78.2 kilojoule. Next term is heat of solution. What is heat of solution? Heat of solution is defined as the amount of heat evolved or absorbed when 1 mole of the substance is dissolved in excess of the solvent. Excess of the solvent. For hydrated salt and for salts which do not form hydrates, delta H is positive plus, and for anhydrous salt it is negative. Again you listen carefully. Heat of solution is defined as the amount of heat evolved or absorbed when 1 mole of the substance is dissolved in excess of the solvent, more solvent. For hydrated salt and for salts which do not form hydrate, delta H is positive, and for anhydrous salt it is negative. For hydrated salt, delta H value is positive, means you have to supply the heat, and for anhydrous means salt which was not having water molecules, in that case delta H value will be negative. For hydrated salt means which salt which have already water is present. Then for hydrated salt and for salts which do not form hydrates, delta H is positive, means you have to supply heat. Delta H value is positive. And for anhydrous salt which has no water molecules, in that case delta H value will be negative. Now next term is heat of fusion. Heat of fusion. Heat of fusion is the heat required to convert 1 mole of solid substance into liquid at the melting point. Very simple way you can define heat of fusion. Heat of fusion is the heat required to convert 1 mole of solid substance into liquid at the melting point. That required heat is called heat of fusion. Now, next term is heat of vaporization. What is heat of vaporization? And heat of vaporization is the heat required to convert 1 mole of the liquid into vapor at the boiling point. Correct? You remember, fusion is at the melting point. Heat required to convert 1 mole of the liquid into vapor at the boiling point. That is heat of vaporization. But in case of fusion, heat required to convert 1 mole of the solid substance into liquid at the melting point. Heat of fusion at the melting point and heat of vaporization at the boiling point. In both cases, 1 mole is required. Always you are knowing all heat of neutralization, heat of hydration, heat of solution, heat of fusion, in heat of vaporization, in all cases 1 mole you are considering, 1 mole. Now next term is heat of sublimation. Again same way, heat of sublimation is the heat required to convert 1 mole of the solid directly into vapor below boiling point. It is equal to heat of fusion plus heat of vaporization. Again I am repeating, heat of sublimation. Sublimation process, you know that without converting into liquid, it will directly go to the vapor. Correct? That is the sublimation. Then heat of sublimation is the heat required to convert 1 mole of solid directly into vapor below the boiling point. This is the condition, below the boiling point, not above the boiling point, below the boiling point. It is equal to the heat of fusion plus heat of vaporization. You add both, heat of fusion plus heat of vaporization. Then you will get the value of heat of sublimation. Here you should know, in heat of sublimation, why it is not converting to liquid, that is the main question. Then I am telling you explanation. Actually, you know that when vapor pressure of the liquid becomes equal to the atmospheric pressure, the temperature at which vapor pressure becomes equal to the atmospheric pressure, then that temperature is called boiling point. But here in case of sublimation, when substance is heated, it will vaporize and will become equal to atmospheric pressure below its melting point. This is the important thing, sir. In case of sublimate that this vapor pressure of the substance becomes equal to the atmospheric pressure below its melting point. That's why it will not convert to the liquid directly, it will evaporate. Then heat of sublimation is the heat required to convert 1 mole of solid directly into vapors below the boiling point. It is equal to the heat of fusion plus heat of vaporization. Then heat of sublimation, here you have to remember that it is the heat required to convert 1 mole of solid directly into vapor below the boiling point. Okay. Now next term is Hess law. His law of constant heat summation. His law of constant heat summation. It is very, very important. Actually, all terms are important. If you know all these terms, then thermodynamics will become easy. Main things of thermodynamics I am discussing. Only these terms are used in full thermodynamics. This is the concept. These terms, if you are knowing, then thermodynamics anywhere, either in general or in biochemistry, means within the body, same thing will happen. Same term will be applied. Then now his law of constant heat summation. What is his law of constant heat summation? Now I am telling you. It states that the total amount of heat evolved or absorbed in a reaction is the same whether the reaction takes place in one step or in a number of steps. Sometimes reaction takes place in 3 or 4 steps. Then all steps you add. Then what is the total heat? Just to make it sum. Or if directly from the initial state to the final state, what is the heat? Then that heat will be equal to the all the heats were sum. You have made the sum of, suppose in 5 step reaction takes place. Then every step reaction heat will be involved or absorbed, whatever be. But total, just to add all heat, whatever is coming, that heat. And suppose now reaction takes place directly from initial to final state. That time heat, or when it will take place in different steps, both heat will be equal. That's why it is called constant heat. Then His law of constant heat summation states that the total amount of heat evolved or absorbed in a reaction is same whether the reaction takes place in one step or in a number of steps. Now, what is the bond energy? Bond energy is defined as the average amount of energy, average amount of energy produced when one mole of bonds are formed from the isolated gaseous atoms, or the amount of energy required when one mole of bonds are broken so as to get the separated gaseous atoms. Average value is taken because energy required to break a particular kind of bond is not the same in polyatomic molecules. As for example, in methane, CH4, CH, 4 bonds are there. Then if you want to break the bond, all 4 bonds, then all bonds, each bond will not give the same energy. Each bond will not give the same energy. Okay, little it will vary. That's why average is used. Average value is taken because energy required to break a particular kind of bond is not same in polyatomic molecules. As for example, 4 CH bonds in CH4, or in different molecules like carbon tetrachloride, or forget, you consider as a methyl chloride CH3Cl, or you can consider ethyl chloride, ethyl C2H5Cl. Then here all bonds are different. CH3Cl, 3 are CH bond, 1 is CCl bond. There in CH3Cl, methyl chloride, 3 H bonds are there, CH, 1 is CCl bond. Hence all will have different energy. Then bond energy just to take the average of all four. And in ethyl chloride also same way, C2H5Cl. Then here also you have to take average. Knowing bond energies of the reactants and products, knowing bond energies of the reactants and products, the enthalpy change of a reaction can be calculated. How it is calculated? Then delta H reaction is equal to summation of bond energy of reactants. Summation, sign of summation sign you have to write. Sign of summation, bond energy of reactants. Okay, that is the total energy, bond energy of the reactants. That's why summation sign is written. Summation of bond energy of reactants minus summation of bond energy of products. Okay, means reactant minus products. Bond energy of reactants minus bond energy of product. That is called delta H reaction. Delta H reaction. That is also called enthalpy change of a reaction. This formula you should remember because it is used while solving the numericals. Then delta H reaction is equal to summation of bond energy of reactants minus bond energies of products. Okay, now again I am repeating, bond energy is defined as the average amount of energy produced when one mole, you remember, 1 mole of bonds are formed from the isolated gaseous atoms. Actually, bond is formed only when atoms will be in gaseous state, not in liquid, not in solid. This you remember, that formation takes place in gaseous state. Okay, then this is the very, very important point. A student confused, they will think that it will form in solid state or liquid state. No, in gaseous state. Then bond energy is defined as the average amount of energy produced when 1 mole of bonds are formed from the isolated gaseous atoms. This is the one definition. Or reverse of this, or the amount of energy required when 1 mole of bonds are broken so as to get the separated gaseous atoms. Already suppose 1 mole bonds are there, then how much energy will be required? The amount of energy required when 1 mole of bonds are broken so as to get the separated gaseous atoms. You can define in both ways. And already I give an example. Average value is taken. Why average value? Already I told, average value is taken because energy required to break a particular bond is not same in polyatomic molecules. Examples are methane, CH bond. 4 CH bonds are there. That's why average is used. All CH bond will require a little different, not too much. And methyl chloride also. Where there are 3 CH bond is there, 1 CCl bond is there. Ethyl chloride also same way. And knowing bond energies of the reactant and product, the enthalpy change of a reaction can be calculated using the relation delta H reaction is equal to summation sign bond energy of reactants minus summation of bond energies of products. Now next very, very important term I am going to discuss, that is the spontaneous process. In thermodynamics or in biochemistry. In biochemistry means inside the chemical reaction inside the body. This term is used, very important term and concept, and Generally, a student will not understand meaning of a spontaneous process. Then now just to listen carefully, quickly you will understand. A process which can take place either by itself or by initiation, independent of rate, is called a spontaneous process. A process which can take place either by itself or by initiation, independent of the rate. Rate here you have to not consider whether it is a slow or fast, that you can neglect it. Here this is not considered, independent of the rate. Then a process which can take place either by itself or by initiation, independent of the rate, is called a spontaneous process. Its example is, many examples are there. You can understand that suppose from the hill water is coming down, then by own it is coming. You are not doing anything, sir. Then this is called a spontaneous process or natural process. Like that way, many reaction, simply if you will mix 2 or 3 substances, then reaction will start. You have to not do anything. You have to not heat. Correct? Simply you will mix, reaction will start by own. Then this is example of a spontaneous reaction. Reaction may be slow or fast. That is different things. I am telling another example. Many common examples are there. Suppose now you have potassium nitrate plus potassium chloride. You take potassium chloride plus silver nitrate solution, KCl solution plus AgNO3 solution. Just to mix it, within a fraction of second, you will get a white precipitate. That is for AgCl. So, silver chloride precipitate you will get within a second, fraction of second. Very fast, very fast. Then KCl plus AgNO3, both are solution. After mixing, quickly you will get white precipitate of silver chloride, AgCl. This is actually example of a spontaneous reaction. Many reaction where just simply you are mixing and reaction is taking place. That is actually called a spontaneous reaction. One more example I am telling you, that take glucose, little quantity of sugar you take. Sugar also you can take, ordinary sugar. And in that you add concentrated H2SO4. Suppose you have taken 1 gram, then 5 ml you can add 5, 6, 7 ml, like that way you can add concentrated H2SO4 in a beaker. Then you will see that now automatically reaction will start and some gas will come out. That is actually carbon dioxide gas. And if you will touch it, then you will find now it is becoming very warm, like hot, very warm. Heat will be produced. Then now you can see, simply you have H2SO4 you have added in sugar solution, in sugar. Even in sugar solution also reaction will take place. Solid sugar will take, then also reaction will take place. This is the example of a spontaneous reaction. And these are the fast reaction I told you. Slow reaction, then this see, now you are seeing a sand that is coming from the mountain due to the weathering. Weathering means when rain will be there, heavy rain will be there, then now you can say big stone of the mountain that will break into very small pieces, and it takes very long time to convert into very small pieces. Then these are the very, very slow reaction. Okay. Then plant you have seen, it will grow slowly. Our children grows from nascent, you can say baby to you can say when it become elder, okay, that time, or young, you can tell it is not in 1 day or 2 days. Slowly and slowly, very slowly, that will grow. Children will grow, baby will grow, just like slowly only. That is also due to chemical reaction. In our body, full chemical reactions are going on. Then this reaction is also, you can't tell very fast, and you also can't tell very slow. It is this type of reaction that is intermediate only you can tell. Many reactions are there. Organic reactions are, or all organic reactions will take time to finish the complete. For the complete reaction, it will take time. What I to give an example of glucose plus H2SO4, that is the now this is organic reaction. Organic reaction, this comes under intermediate, neither fast nor slow. Okay, then all these reactions, for the, you have to, that reaction, but that which will take by your own, you have to not do anything. That type of reaction is called a spontaneous process. Now, what is actually this thing, non-spontaneous process? Then reverse of this, when you have to do something for the reaction, then that is called non-spontaneous. Here, in a spontaneous process, you have to, one more thing, you can understand, initiation. One step is there, initiation. Means just slightly you have to initiate the reaction. After that, automatically reaction will take place. Just like you can say wood, you know, that very thin wood, may suppose large quantity of that type of wood is there, very thin. Actually, when carpenter will work, that time we'll see again very thin wood will be there. At that time it will be produced. Then that type of wood I am talking you, small pieces, very small pieces and thin. If we will put a small fire, then obviously it will catch fire and all wood will burn. Correct? Then sometimes for the reaction, just you have to initiate slightly, then automatically reaction will continue. Okay? Means something you have to start, after that reaction will take place. Then that is also initiation step is required in a spontaneous. Okay? And then obviously reaction will continue. And here non-spontaneous means a process which can neither take place by itself nor by initiation. Neither by itself, will not take by itself nor by initiation, is called a non-spontaneous process. Just you can think one example. Suppose now from the ground you have to take water from 14th floor or 13th floor. How will you take? Then motor is required. You have to apply too much force. Then water will go from you can say surface to upside, or from the ground to top floor. Or water you can't send from land to top mountain. From water you will not go from ground to the top hill. You have to do some things. And this type of things for non-spontaneous reaction, you have to do so much practice. You have to apply so much condition. Only then some chemical reaction will take place. Then main condition is temperature and pressure. You have seen that in many reactions temperature is required, pressure is required. It means that reactions are non-spontaneous. Non-spontaneous. It requires heat and pressure. Some conditions are required. Sometimes catalyst is required. Then a process which can neither take place by itself nor by initiation is called a non-spontaneous process. The overall driving force for a process is the resultant of the overall driving force, net driving force for a process. Some reaction is going on. Here process means reaction process. The overall net driving force. Actually, for the reaction, one force is required, that is called driving force. The overall net driving force for a process is the resultant of two factors. First factor is tendency for minimum energy. Tendency for minimum energy. Actually systems wants to become, they want to lose the energy. They want actually to have minimum energy. That's why reaction will take place. Then first factor is tendency for minimum energy, and second tendency for maximum randomness. Random. They want to become free. They want to move here and there. No restrictions required. It is their natural tendency. Then due to these two factors, tendency for minimum energy and second tendency for maximum randomness, that is the actually driving force. Driving force depends upon these two forces. Okay, the overall or net driving force for a process is the resultant of first tendency for minimum energy and second tendency for maximum randomness. Now come to the very, very important term, entropy. Entropy, E-N-T-R-O-P-Y. E-N-T-R-O-P-Y, entropy. Then actually in entire thermodynamics, second law of thermodynamics, that is based on entropy only. And in thermodynamics, entropy is very, very meaningful and very, very important terms. What is actually entropy? Then listen carefully. If you will not understand entropy, you will not understand thermodynamics or second law of thermodynamics. Now I am telling you, entropy is a measure of randomness of a system. Randomness of a system. You can understand why one example you can tell. Actually, entropy is also called times arrow. Times arrow. Concept of time has come from the entropy. Now, just to understand what is actually entropy, in a simple example I will tell you. You can apply same things on the molecules or in any substance. Now suppose in a school or college, suppose 60 students are there in a classroom. Then you know that in classroom all students will, suppose in one bench 6 students are sitting and 10 benches are there. Then 10 into 6, 60 students are sitting in a proper way. Correct? All students will be sitting in a proper way. And suppose after the class, suppose class is over, then what you will see? You have already observed that now students will be not sitting in the one place. They will turn, some student will, first of all, some student will leave the place, leave the bench. Some student will turn left and right, back side. Correct? Means all students will change their position. All students will change their position. They are not now in original position. Then this actually this change, this now you can say because all students left their position or trying to leave. Some things they are not in a fixed position. They have changed their position. Then how much they have changed the position? How much? Someone will leave from the class only. Someone will be in the class. Majority of them will be in the classroom only. But they will be moving little here and there. Correct? They will not leave. Sometimes only they will stand and will be talking. Then this actually, this change, how much they changed, that how much, that is actually entropy. How much they have made a change. How much they have made a change, that is the measurement. That measurement is called actually entropy. How much they become disorder. Measurement of disorderliness, that is entropy. Entropy is the measure of disorderliness, means how much they become disorder. In a crystal, all atoms will be arranged in a proper way. All atoms will be arranged in a proper way. Any crystal. But when you will heat, then now these atoms which was properly arranged, now it will disturb. It means entropy increased. Entropy increased. They are not in a proper position. Means they are trying to leave or may leave also from their original position. Then how much they have made a change? How much disorder took place? How much? That how much change took place? How much disorder? Mainly disorder. Okay. How much disorder took place? Arrangement disturbed. That is actually called entropy. Entropy change. Then in a crystal form, they will be properly arranged. Means entropy will be zero, like that way. But if you will heat, then little disturbance will be there. If you will heat more disturbance will be there. If you will heat again further more, then they may convert from solid to liquid. Then now entropy change, entropy is increasing. And again you will heat the liquid, it will convert to vapor state. Further entropy changed. Means now we can say atoms fully now disturbed, ordered change completely. Then how much they become disordered, that is actually called entropy. I think now you have understood. Now one more example I want to give you. I told you that entropy is the times arrow. We see watch, now it's 2 o'clock or 3 o'clock or 6 months, 1 year, what we are telling. This concept has come from entropy. You will ask how? Then see what happened. Actually time concept is not very old. It is new only. When science came, now our minute, all the things, it is not very old. 300, 400 years back only when science came, after that only. Before that, time concept was different. Shukla Paksha, Krishna Paksha, that was where from the moon, 15 days dark, 15 days rising moon. Correct? 15 days rising moon. And 15 days, now moon was cutting and finally it will be dark. Correct? That is when moon is rising, becoming more and more, you can say lighted, that is called Shukla Paksha. And when it is becoming slowly and after the full moon is called Purnima. Then full moon. After that slowly it will become less and less and less. Finally it will be fully dark. Correct? Then that is actually full moon, you understood? Like that way finally it become dark. Correct? Then this change, this was the concept. Then dark, second half, that was called actually Amavasya. Dark means Amavasya, and full moon means this Purnamasi, full moon, full means Purna means full, complete, Purnamasi, and dark means Amavasya. Then that was the calculation in ancient time. That was the only calculation. 15 days Shukla Paksha, 15 days Krishna Paksha. Then now I am telling you how this entropy became the this times arrow. Times arrow. Actually, when Earth was moving around the sun, that time sign was not there. In the beginning, nobody was considering. Simply, Earth was moving around the sun. But scientists observed that now this Earth position is changing. Earth position is changing. It is going from one place to the other places. It is moving, and finally it is reaching to the original place. Then this gap from starting from original, again slowly after moving, reaching to the same. This gap they have considered as a 1 year. And then after that, 1 year divided into 12 months. After that, And 1 month again, 1 month means 30 days is considered. It is divided into 30 days. Days converted into 1 day means 24 hours. Hours converted into minute. Minute converted into second. All things you know. Second also now it is in fraction. Then see how this entropy concept has been given the concept of time. That's why it is called times arrow. Now entropy change. Then now you can understand entropy will also change with time, or with you can say in reaction when you will make change in heat or pressure. Then now there will be change in entropy. Then here in thermodynamics, already told you, change has importance. Absolute value of entropy you can't understand, you can't determine. It is impossible. It is impossible to determine absolute entropy. All entropy, absolute, all thermodynamic parameters you can't determine. Then here also entropy change is there. Entropy is now represented by S, capital S. Then entropy change, that is the S1 minus S2. Or you can tell initial is the S1. In the beginning, what was the order? And after in the final, what was the order? Means how disorder took place. That change. Then S2 minus S1, that is the delta S. That is called entropy change, delta S. Then entropy change during a chemical reaction or during a process. Entropy change during a process is defined as the amount of heat evolved or absorbed isothermally and reversibly divided by the absolute temperature at which the heat is evolved or absorbed. Here you should know temperature is constant isothermally. This is the condition. The heat will change, temperature will remain same. Correct? Because there will be internal change. It will not allow to make because process is isothermal. Temperature will not change. Heat inside heat will change. That will bring the disturbance. Actually, when we will supply the heat, very important things I am telling you. When you apply the heat in any system, in any reactant, then first it will become warm. Inside that it will become warm and expansion will take place. And if you will not allow to expand, then actually little heat will be used up. in expansion. After that, temperature will rise. Correct? Then like that way, first inside some disturbance will be there. After that, temperature will rise. But here you are not allowing to raise the temperature. Suppose you are keeping isothermally. System is isothermally. Then entropy change during a process is defined as the amount of heat evolved or absorbed isothermally and reversibly, because reaction will be generally reversible. A small any step you can see, it will be reversible, means reactant to product, product to reactant. You can divide one reaction in many steps. Every step reaction will be reversible. Okay, this is another condition, isothermally and reversibly. And temperature you are keeping constant, means this change, entropy change means entropy change during a process is defined as the amount of heat evolved or absorbed isothermally and reversibly divided by the absolute temperature at which the heat is evolved or absorbed. Means delta S is equal to Q. You can say isothermally and reversibly. Q means heat. Q by T. Q upon T. Q is heat upon T. That is the temperature at which heat is absorbed or evolved. That temperature you have to divide by that temperature. Then Q delta S is equal to Q upon T. But simply you can't write. You put both condition. A small q down, both condition you write. First write isothermal, ISO, comma. Second condition reversible, REV, reversible, shortcut. Then you should write Q, REV. A small q down you write REV. Or first write ISO, isothermal, comma, REV divided by T. That is equal to delta S. That is the entropy change. Then entropy change is equal to Q divided by T. What are the condition? Q should be isothermal and reversible. Don't forget. Q ISO. That's why it is written in shortcut. You will not forget. Q ISO REV divided by T. Now, what is the unit? Unit of entropy change. Then entropy change, I told you, that is the heat change. Heat evolved or absorbed. Then heat, how will you measure? Then in a joule, you will measure in joule per Kelvin, because you are dividing by temperature, absolute temperature, then per Kelvin. Correct? Then heat, for the heat joule you will write, and you are dividing by temperature. That's why temperature, Kelvin, you are measuring in Kelvin. Then joule per Kelvin. And how much you will take, how much you are considering. Then here 1 mole you are considering. In chemistry always you are considering 1 mole per mole. Hence its unit will be joule per Kelvin per mole. Remember, unit is also, question is asked, joule per Kelvin per mole. Okay. Then this I told you entropy of units of entropy change. Now on the same basis you can define entropy of fusion, because in fusion also there will be disorder. In every step, in any change, entropy will be there. You remember, when your reaction is, why entropy is becoming important? Because in reaction phase change will be there. Solid to liquid, liquid to vapor, sublimation, many things will be there, many process will be there. Then every time disorder will be there, then every time change will be there. That's why every time entropy change will be there, change in entropy. Then here entropy of fusion, same way you can define what I have discussed, heat of hydration, heat of fusion, solution, like that way. Same way you can tell entropy of fusion. Then here fusion means a small f, delta H f, a small f, just delta H is capital, and below H you write a small f, means fusion. Then entropy of fusion means, now same type of definition, enthalpy of fusion divided by fusion temperature. Same things, enthalpy of fusion divided by fusion temperature. Then delta HF divided by delta TF. Then here delta HF means enthalpy of fusion divided by TF. TF means fusion temperature. Same way entropy of vaporization. That is the, now for the vaporization you will use the term small v, delta H V, UV. V means vaporization. In shortcut you can write delta HV, means heat entropy of vaporization is equal to, again same way, enthalpy of vaporization. How much you can say enthalpy is there during vaporization divided by boiling point. Here for the vaporization, boiling point you will use divided by boiling point. That is the delta HV divided by TV. Here T, a small b, a small b means boiling. Then delta HV divided by TV. That is called entropy of vaporization. The entropy of vaporization is represented by delta HV. Now further, entropy increases. Now again you remember what I have listened carefully. Entropy increases when solid changes to liquid. Correct? Entropy increases when solid changes to liquid or liquid changes to vapors. In gaseous reactions, if also, actually, remember when solid changes to liquid, entropy increases. And when liquid changes to vapor, then also entropy increases. In gaseous reaction, it also increases when number of moles of products is greater than reactants. From the reactant, you will get product. Correct? From the reactant, you will get product. Then sometimes you will find number of moles of products are more. Number of moles of products are more than reactant. How? Then you take the example HI, hydrogen iodide. HI, when it will break, it will form H2 and I2. It will form H2 and I2. Then only HI means only 1 mole. But it is giving hydrogen gas and iodine gas. Then now if you will count that number of moles, then if we will consider only HI, then reactant term, now it is giving 2, iodine 1 and this hydrogen gas 1, 2. Actually in balanced equation it will look same, no change. But now you consider this ammonia gas, formation of ammonia gas, then it will be more clear. Then ammonia gas, then here N2 plus 3S2, N2 plus 3S2, total how many molecules are there? N2 means 1 mole, 3S2 means 3 mole, 3 plus 1 4 mole, and product is giving 2NH3, N2 plus 3S2, that is the 2NH3. Now it is a balanced 2NH3, 2 nitrogen, 6 hydrogen. But mole wise, here reactant side 4 mole and product side only 2 mole. then there will be change in number of moles. It here in this case it is decreased. And suppose when there is a decomposition of ammonia, decomposition means when ammonia will break, then 2NH3 will require. You will get four molecules, one mole nitrogen and 3 mole hydrogen gas. Then products sometimes may increase or decrease. Number of moles may increase or decrease. Then accordingly entropy will change. Okay. Then entropy increases when solid change to liquid, liquid change to vapors, and in gaseous reaction it also increases when number of moles of products is greater than reactants. Example is PCl5, phosphorus pentachloride. When it will break, when it will dissociate, it will give PCl3 plus Cl2. 1 mole is giving 2 mole. Now again very important concept I am going to discuss. Gibbs free energy. Gibbs free energy, capital G, it is denoted by capital G, and change is denoted by delta G, capital G. Then Gibbs free energy, what is this? Gibbs is the name of scientist. Free energy, name itself is called free energy. In simple meaning of free energy, that energy available for energy available to do work. Energy available to do work, that is called free energy. You remember, available energy for work, to do the work, that is called free energy. And this is due to Gibbs. Gibbs is the name of scientist. That's why it is called Gibbs free energy. Helmholtz free energy is also there. Same concept, correct? There Helmholtz energy means there other than, you can say, work of expansion. Many works are there like electrical work. Then in that case expansion will be not there. There Helmholtz, that time it will be called Helmholtz energy. But if expansion is there, volume change is there, then that time you can Gibbs free energy will be applied. And when other than volume change is there, I give an example, electrical work done, then there Helmholtz energy is considered. Then Gibbs free energy of a system is given by how? You remember this formula, very important formula. G is equal to H minus T into S. Means it is the relation between three-term relation. Three-term. G means Gibbs, H means enthalpy, and S means entropy. And entropy is related to temperature, you know. Hence, total 4 terms are there. G is equal to H minus T into S. Wherever S will be there, T will be there. Okay, don't bother, don't think too much. There mainly 3 things are there. G, H and S, all 3 are related. Temperature also you can consider, but it will be always with entropy, means S. Then G is equal to H minus T into S. T into S always. Then G, you know, that is the Gibbs energy. H is enthalpy and S is entropy. Hence Gibbs free energy of a system is that thermodynamic quantity. It is thermodynamic quantity of parameter. Gibbs free energy of a system is that thermodynamic quantity. Okay. What it will tell? It will tell about decrease, a minus sign. Always will come minus sign. Then here Gibbs free energy of a system is that thermodynamic quantity that decrease on whose value during a process is equal to the useful work done by the system. Hence minus delta G is equal to W useful work. Useful work. Correct? Then I told you useful work, remember. Then minus delta G, because system has work done. System, just like you will do the work. Correct? Then there will be heat loss. Any system. If system is doing work, then minus sign will be there. Already I have discussed. If you can say on system work will be done, that time there will be positive sign on. But by means, by system is minus. Then here minus delta G means work has been done by the system, and that energy, heat loss, whatever happened, that is equal to useful work. That energy converted to work, useful work. Hence, in a shortcut, you can remember minus delta G is equal to W, useful. W, there you can write down useful work. Hence, G is equal to H minus T S. G is equal to H minus T into S, or TS also you can tell. This is the relation. Okay, only on that basis. Now for every terms you put delta. For the G you write delta G. For H you write delta H. For T will be the same. Not only for S you can write delta S, because at a particular temperature, this entropy, for the entropy, absolute temperature, one fixed temperature is required. Hence delta T will not work. Only T will be there. Then G is equal to H minus TS. Then delta G is equal to delta H minus T into delta S. You can write change in free energy like this way only. Correct? Then change in free energy during a process is given by delta G is equal to delta H minus T into delta S. This equation is called Gibbs-Helmholtz equation. Delta G is equal to delta H minus T into delta S. This equation is called Gibbs-Helmholtz equation. Helmholtz equation is only Helmholtz equation is different. Here Helmholtz also applied, because both have done the work for you can say this energy, free energy. For the energy, free energy, both have done the work. Then here both concept is applied. That's why this equation is known as Gibbs-Helmholtz equation. And today I am stopping only here. Next class again I will continue. Many terms, I think 75%, more than 75% terms I have finished. Actually I am reviewing the chapter. Correct? Everything has details, but I am reviewing the chapter. Correct? Exam time it is helpful. And if you have studied in details, then if these terms will be in your mind, then you can write any answer if concept is clear. Then now I am stopping only here. Thank you.